Thanksgiving, so we're not going to have class next week. My experience is that there's so many people traveling that it's kind of fruitless to have class because then half the people miss the class and then I have to repeat everything anyway. So I've learned from experience it's much easier to just not have any classes on the week of Thanksgiving. You've earned it anyway. I've worked pretty hard, right? So no class next week. All right. And then today, we're taking on a kind of a controversial topic. Set on lecture notes 14. This is Bayesian Inference. So we finished the stuff about the bootstrap and so on. So this is a more philosophical topic in some sense. Before I plunge in, are there any questions about anything before we start? Okay, you'll notice, by the way, that there's in lecture notes 14, there's a couple cartoons. There was a cartoon from that guy who does XKCD, and that was about Bayesian and frequentist inference, and that was when I had a blog, which was quite a while ago. So I also put a response cartoon in my blog, so you can have fun looking at that later on. But what are we talking about? So everything we've done so far in this course has been what's usually called or classical inference, which is sort of the dominant view of inference in statistics at least. And but there's a different view, which we should talk about too, which is called Bayesian inference. It's quite different, although there are some similarities. Actually, let me do it. So let's top of page 4. I'm going to copy that table. Let me create a table here. So what is this? There's a lot of confusion about what these things are and what they're not. They're really just two different tools, and people get confused between them. It's very easy to get confused. In fact, until I show you some specific examples, it's actually kind of hard to distinguish them, but they are quite different in some examples. Some examples are very similar. So in frequentist difference, this is what we've been doing all along. Probability refers to frequencies, right? When I say probability of heads is a half, we mean if you flip a coin many times, you get half in some limiting sense. And in particular, confidence intervals are talking about if many people use this procedure, 95% of them will drop the true value. It's about repetition. That's what frequentist inference is about. In particular, data are random and parameters are just fixed unknown quantities. Bayesian inference, which is not to be confused with the Bayes rule that we talked about earlier, that's quite different. Bayesian inference refers to a different way of thinking about it, where probability is regarded as a subjective degree of belief. Everybody has their beliefs and they're quantified by probabilities. It's nothing to do with frequencies. What I'm going to show you is that they can be very, very different. And it's not that one's wrong or one's right, they're just different things. In fact, the biggest confusion, I think, comes about because we use the same symbol. We use P to mean probability, and of course, mathematically, that's fine because the axioms of probability are the same. If we used, I don't know, B of A for degree of belief and F of A for frequencies, there would be no confusion about, I think, or very little confusion about Bayesian versus frequentist statistics. But because we use the same symbol, people sometimes think degrees of belief should act like frequencies and frequencies should act like degrees of belief, and they're just very different animals. So I think a lot of the confusion is just from maybe bad terminology. The name comes from Bayes' theorem, which also has nothing to do with Bayesian inference. Well, it's not, I shouldn't say it has nothing to do with it, but not as much to do with it as you might think. Bayes' theorem was proved by this guy, Redmer Bayes, in the 1700s, so that's why it's called Bayesian inference. And so what is Bayesian inference? Well, first of all, let's talk about what it is. Conceptually, it's very simple, and we've already done it, although we used it for frequentist purposes. This is why it gets confusing. In Bayesian inference, again, we think of everything as, we have subjective probabilities. Since we're dealing with subjective probabilities, not frequencies, you can make everything's got a probability distribution, including fixed parameters. See, in frequentist inference, a fixed parameter can't have a probability distribution because it's fixed. It's not wobbling around. But if you take the subjective view, that it's just your opinion about something. Well, you can have an opinion about a fixed quantity or data or anything, so you can put a probability distribution about anything. And so in Bayesian inference, the procedure is pretty simple. You put a prior, P theta, that's your prior beliefs, your degree of beliefs about theta before you see the data. This is not like when we put a prior before to derive a Bayes estimator, which ended up being minimax. That was just a mathematical device. The prior had no meaning. Here, this is actually supposed to represent your degrees of belief about the parameter before you see the data. And then we have the model, or the likelihood, which now we regard this as your degrees of belief about the data given theta. And then we do typically use Bayes' theorem to get the posterior distribution. So we know what that is. The posterior is proportional by Bayes' theorem to the prior times the likelihood. And now that posterior distribution represents my beliefs about theta conditional on the data. And now I can use that for whatever I want. I can make a point estimator or an interval estimator, but the interpretation is very different. These are subjective degrees of belief, nothing to do with confidence intervals or frequencies. So even though the mechanics here are very simple, and they're the same as what we did to get Bayes estimator before, the interpretation is quite different. Okay, so the interpretation here is, again, it's your degree of belief about theta. So in particular, if this is your posterior distribution, let's say that's your posterior right here. And if I find a set A that has probability 1 minus alpha, the interpretation is that your belief that theta is in A given the data is 1 minus alpha. It does not mean that if you repeated this, it would cover it 95% of the time. That's a frequency statement. So the interpretation is very different. And one of the things I put at the front of the notes is that Bayesian inference does not refer to using Bayes' theorem. You can do Bayesian inference without using Bayes' theorem. You could just, since it's subjective degrees of belief, you could just look at the data and say, now I'm going to say what my beliefs are about theta, and just state what your posterior is. Nothing to stop you from doing that. That's a perfectly legitimate thing to do. You don't have to use Bayes' theorem. And conversely, in frequentist inference, we often do use Bayes' theorem to get a good frequentist estimator. For example, minimax estimators are Bayes estimators. But they're not supposed to represent anybody's beliefs. It's just a mathematical device to get something with good frequentist properties. So you should not think of Bayesian inference as using Bayes' theorem. They're two different things. Yeah?
What is the relationship between the posterior and the parameter and the estimator that we have calculated as posterior, like calculated posterior distribution?
Well, we could compute the mean of this, and that would be your Bayesian point estimator. That would be the posterior mean. That would be a typical Bayes estimator, for example. But now the interpretation, again, is that it's representing a summary of your beliefs. So you just think of the posterior as representing your belief, and you can summarize it any way you want, like taking the mean or the median and so on. Okay. But this confusion about Bayes' theorem being the same as Bayesian inference is very pervasive. There's a whole book by, I forgot her name, very scholarly, nice book about the history of Bayes' theorem, but she's continuously confused about the difference between Bayes' theorem and Bayesian inference. And she keeps saying people are opposed to Bayes' inference, and then she talks about Bayes' theorem. And my favorite example of this is Nate Silver, who's in the news a lot lately. His book, The Signal of Noise, great book, but throughout the book he goes on and on about how he doesn't like frequentist inference, which he somehow equates with p-values. He seems to think p-values equals frequentist inference, but p-values are one tool in frequentist inference. And he uses Bayesian inference, he says. But then when you look at the rest of the book, he's obsessed with checking the frequency properties of his predictions. He wants, when he predicts rain 60%, the probability of rain is 0.6, he means it should, on similar days, it should rain 60% of the time. If you saw the controversies he was in over the election, he kept talking about how well-calibrated his predictions were. That's frequentist thinking. He's using Bayes' theorem, but he's clearly doing frequentist inference. He wants the frequencies. He wants to be right 95% of the time. That's a frequency concept. So you can see this subtle distinction gets lost all the time. And when I do some examples, it'll be clear, because right now it might not be obvious that if I compute a posterior distribution and find a region that has 95% posterior probability, the idea that that won't have 95% coverage might seem a bit weird. But I'm going to show you very specific examples where the coverage, how often does it cover the truth, versus the degree of belief, are just very different quantities. And it's not a statement that one is right or one is wrong. They're just different tools. Right? Here's the thing. If you want to analyze subjective degrees of belief, Bayesian inference is the correct tool to use. If you want procedures that have certain frequency guarantees, like covering the truth 95% of the time, consistency or minimaxing, whatever, then you use frequentist methods. They're just different tools. And I think a lot of there's a lot of fighting that goes on between people on these different things. And I think the fighting goes on because of the lack of understanding that they're answering two different questions, really. And this controversy, it goes on in statistics, but it goes on in every field. Like I work with astrophysicists, and there's a lot of debate there about should they be using frequentist or Bayesian methods to analyze astrophysics data. And it's pretty clear, again, that very smart people get very confused about this because they're missing the point. Again, the goals are quite different. I'll just tell you a true story. A colleague of mine, an astronomer, very, very smart person, came and said he'd come up with a way to analyze a certain type of data, and he thought there was something wrong. So I said, okay, tell us about it. And he came up with this Bayesian method, and I think I even mentioned this story earlier in the course. He came up with a method for analyzing a certain type of astronomy data, and it was a Bayesian method, and it looked perfectly sensible to me. He had to construct the prior, wrote down the likelihood, he got the posterior, it all made perfect sense. So I said, what is it you're dissatisfied with? He said, it's not working. I said, what do you mean it's not working? You're doing it correctly. What happened then was he simulated some data, or he knew the answer, and he kept simulating it, finding out that his 95% posterior Bayesian intervals were only covering the true value about 60% of the time. And I said, that's because you're constructing a Bayesian procedure, but you're asking it to have frequentist properties. These are two different things. And then it was something he knew, of course, intellectually, but it was the first time I think it had kind of hit him, that they were really actually quite different goals. So it's just important to keep these goals separate. So I have this little table that summarizes this. I'll put it up here so we can look at it. So first of all, there's what is probability mean? This is a deep philosophical question. I don't claim there's one right answer here, but in the Bayesian view, it's a subjective degree of belief. So what does that even mean? Well, I'm not actually 100% sure myself, but you know, it's sort of like if I ask you, is it going to rain 50 years from now on January 1st, something like that? You know, you could say, well, I don't know, I think there's like a 70% chance it's going to rain. I mean, you might have an opinion about it. You're not claiming anything about being right, you know, some fraction of times. You're just saying that's your degree of belief, right? Or think of some historical event that happened hundreds of years ago. You might have some, say, I think it's 90% true, 90% that it's true. And people often view these as betting rates. What would you be willing to bet on this? But the point is, it's got nothing to do with frequencies. It's just your degree of belief. It's just a number between 0 and 1, where 1 means you're certain and 0 means you're not certain. And the important thing is, the word subjective means everybody can have their own degrees of belief. You don't have to agree on it. Whereas in frequentist inference, we're interested in frequency, in probability, in terms of limiting frequencies. You know, a 95% confidence, and we're talking about, again, if billions of people use my software, about 95% of them would contain the true value. That's a frequency. It's over the whole population that's using this thing, using this procedure. Okay, so that's one difference. The main difference, though, once we say that probability is regarded is what's the goal of these? The goal of this is to analyze, or to quantify beliefs. The goal of Bayesian inference is you try to analyze your beliefs by stating what you think the prior probabilities are, And then you typically using Bayes' rule to get the posterior, although you don't have to do that, but that's typically what's done. And then, so in other words, updating your beliefs once you have information. And so, in some sense, it's belief analysis, you might say. And you can imagine, just as a simple example, if you're doing a clinical trial on some medication, and you might have a lot of prior information about this medication. So you might already start off by knowing that the difference between the treated and the placebo maybe should be about 0.7, and you might have information that you could try to quantify into a prior distribution. So you can imagine cases where you would have a lot of prior information, and quantifying that might be quite useful. But in frequentist inference, there's no claim about analyzing beliefs. It's just creating procedures with long-run guarantees, procedures with frequency guarantees. So this could be consistency, mean squared error, all the stuff we talked about. The best example is confidence intervals, which we claim will contain the true value 95% of the time. If you take one of these confidence intervals, the best way to think about it is simulation. If I simulated data from the model, you can construct the confidence interval and ask that it contain the true value, and I repeat that over and over, it will contain the true value 95% of the time, because that's what it was designed to do. That's the goal of frequentist inference. Yeah?
So if you end up getting like a Bayesian estimate and it's consistent with your beliefs, but it's not really, if it doesn't have frequentist property, what's sort of the point of it?
That's a great question, and that's what we're going to talk about, what the disagreement is and what it means. So that's a great question. We're going to come to that. Okay, a parameter, but let's keep going in this table. A parameter, that's a random variable in Bayesian inference, because everything's a random variable. Anything that you have that you don't know is a random variable. You know, did Lee Harvey Oswald kill John F. Kennedy by himself, or did he have an accomplice? That, some people might say, I'm 90% sure he did it alone. Someone might say, I'm 10% sure. That's a parameter, theta, that it had an accomplice or not. It's regarded as a parameter, and you can put a probability on it. Whereas in frequentist inference, it's not. It's just a fixed, unknown parameter. It's not something we put a distribution on. We don't know what it is, but it's some unknown value. On the other hand, the data, x, the data, both methods treat that as a random variable. And this is really, I think, what summarizes the difference between Bayesian and frequentist inference. And again, Bayes' theorem is not the key thing. Bayes' theorem may or may not be used in either case. It is commonly used, of course, in Bayesian inference, but that's not what makes it Bayesian. To me, the big thing here is the goal, which is treating probability as subjective belief and quantifying those beliefs, or creating procedures with long-run answers. This is the difference. So, yes, the key question that was just asked is, what happens when they agree? A lot of times these things agree across, but sometimes they disagree, and what do you do when they disagree? Let's just go, we've already looked at the mechanics of Bayes. I have in the notes a review, which is really nothing more than what I just put up there, which is somehow you have to come up with a prior distribution, then you just multiply it by the likelihood, and that's, conceptually, you're done. You now have the posterior distribution. Now, of course, what do you do with the posterior distribution? Well, you need to summarize it. You might want to find an interval with 95% probability. You might want to find a point estimator like the mean. And there are really interesting methodological questions, which are something we don't talk about in this course. But like, for example, if theta was high dimensional, so theta would be theta g, and I can certainly get the posterior for theta. Just write down Bayes' theorem again. Likelihood times the prior. But now suppose I really want to do inference for theta 1. Suppose I'm really interested. Well, we can use the tools of probability, right? I have a distribution for all of them. How do I get the distribution for one variable? We just go back to elementary probability. I just integrate out the other parameters, right? So I can now compute the posterior for theta 1 by taking the posterior for all the parameters grading out all the other parameters. Now in practice, this could be really hard. This posterior distribution might not be any known distribution, it's just some function. It might not be like a normal or a gamma or something, it's just some function. It could be some complicated function. Not only that, if D is high dimensional, we have some sort of high dimensional integral to do here. So what's happened in the last 20 years, which is quite interesting, is people have developed techniques for dealing with this. The most common are simulation techniques called Monte Carlo Markov chain methods, and some of you will have seen in other courses. So I'm not going to talk about MCMC in this class. Where do we talk about it? I'm sure there's some classes where we discuss it. It's quite interesting stuff, because quite apart from Bayesian inference, just the general question of how do you simulate from a complicated distribution has received a lot of attention in the last while, and there's some really interesting theory and methods there. But what I want to say here is just that, although I've written it down like an integral, in practice, most often people are going to simulate from the distribution. So rather than actually doing the integral, you're going to end up with a simulation, and you can just look at a histogram of all the values of theta 1 that you get from your simulation. And so now you'll have a simulation from this distribution, and you can do everything you want from the simulation. You can find the mean, you can find a 95% interval, and so the most common thing that's done in complicated models these days is to do some sort of simulation method. Okay, for our purposes, all we need to know is that such methods exist. There are cases, of course, that we saw earlier where we know the answers in closed form. I put them back on page 5 for you. We're not going to go through them again because we've already done it, but remember that if you have a Bernoulli likelihood and a beta prior, we computed analytically that the posterior is a beta distribution. Or if you have a normal prior and a normal likelihood, you get a normal posterior. Okay, if you have forgotten those calculations, this is a good time to remind yourself. So just at home, go through, I did some of the examples again, we've done them before, but just remind yourself that in some special cases we can actually compute the posterior in closed form. It's actually a pretty small number of cases that we can do that, but there are cases where we can do it. So, you know, if we can, obviously that's better than having to resort to simulation, but more often than not these days, people resort to simulation methods. Okay, so the mechanics of Bayesian inference are pretty easy. Just conceptually, multiply the prior times the likelihood, but now these philosophical questions arise. And I think the first question, before we talk about what do we do when they disagree, we should talk about a more fundamental question first, which is, how do you get the prior distribution? Where does this prior? And the answer depends, well, I guess it depends on who you ask. So, when you ask statisticians who do a lot of Bayesian inference from the older generation, let's say, they'll say it should come from what they call elicitation, where they would sit down with a doctor and say, tell me how likely you think it is that theta is between this and this. They would literally try to construct a prior distribution truly representing some expert's subjective degrees of belief. That's okay when you have one or two parameters, right? So that's why I said the older generation, because they never did any high dimensional stuff, those guys. So they had easy problems. Oh, just kidding. But you can imagine that in a lot of problems, where are you really going to get this prior from? Especially when, you know, it's 10 parameters, 20 parameters, 50 parameters. Where are you going to get this prior from? So I think this is one of the weaknesses of Bayesian inference, is it's not clear what the answer is. There was a period of time when people tried to formally define, why don't we take a prior that represents ignorance, that represents no prior information? The problem with that is there isn't one. Trying to find what people call a non-informative prior is a little bit like trying to find a perpetual motion machine in physics. You know, people would always come up with a machine that they claimed had to do perpetual motion, and then some physicists would always find a flaw in it, obviously, because it would violate the second law of thermodynamics. It's the same with priors. Somebody would publish a paper saying, here, this prior truly represents no information, and then you could easily show that that just isn't true, because after all, the distribution is supposed to represent prior information. I mean, so going back far in history, Laplace suggested that we should use like a uniform prior to represent ignorance. So if you think about a Bernoulli, and this is what Bayes did too, which is take the prior to be uniform. The problem with that is it's not transformation invariant. So if I take a uniform prior theta, what happens if I look at, say, psi, which is log theta over 1 minus theta? There's nothing sacred about theta. I can look at any one-to-one transformation of theta, and that's just a re-expression of the parameter. And if we do a change of variables, if I start with this and I said do a change of variables and find the distribution on the side, you'll discover it's far from uniform. It's not a uniform distribution. So if I want it, if uniform was supposed to represent no information, but now I have a non-uniform distribution on this thing, how did that happen? I don't have any information about psi. If I don't know anything about theta, I don't know anything about psi. So in other words, on which scale should it be uniform? It's not clear. There's no answer to that. So people sort of abandoned that idea. Perhaps the most commonly used non-informative prior is what's called Jeffreys prior. Jeffreys was a physicist in the early 1900s who also wrote a book about Bayesian inference. And he suggested the following prior. I'll just write it down in one dimension. It's called Jeffreys prior. He said, take the Fisher information and take the square root. And the reason for doing this is it solves this invariance problem. If I do that and I do a transformation of variables, I'll get a new prior. But if I had just done this Jeffreys prior on the new scale originally, I'll get the same prior. So the rule is invariant transformation. So that's a commonly used thing. The problem is, again, once we get to high-dimensional problems, there's lots of examples where the Jeffreys prior just gives posteriors with properties that people don't like. It just turns out to not work very well in a lot of problems in some practical sense. So I think the answer is people pretty much use whatever prior they find convenient without a lot of justification. And so this is one of the criticisms that gets leveled against Bayesian inferences. The prior seems somewhat arbitrary in most cases. But people do use flat priors sometimes. And an interesting thing happens too, which is you get improper priors. I mentioned this once very briefly. What do I mean by that? Suppose we go to our normal problem. The most commonly used prior is to take it to be proportional to 1. That's not a real prior because that doesn't integrate to 1. In fact, it integrates to infinity. Nevertheless, if I just formally go through the mechanics of Bayesian inference, if I multiply that prior times the likelihood, I get a perfectly well-defined posterior. So that's called an improper prior, and it often leads, even though the prior doesn't quite make sense, it often leads to posterior distributions that have good properties. So that's a very common thing you'll see people do, is they'll use improper prior distributions. Yeah.
Regarding your first point about changing the parameter, so normally you can also do the same with entropy, which actually has an interpretation for us, which means information, and then entropy would change. So
That's correct. It's also not invariant.
So, but then you're criticizing the whole concept of interpreting what we are getting out of something, and like you can criticize entropy like that.
Well, it depends what you're using entropy for. First of all, entropy comes up in physics, where it's got a very clear meaning, right?
I'm talking about coding theory, not.
Oh, coding theory. Well, so there are cases certainly where using entropy for various reasons in information theory makes perfect sense. But that's different than saying it's defining a rule for choosing a prior distribution in Bayesian inference. There was a big advocate by the name of Ed James, who was a proponent of using maximum entropy, for example, in Bayesian inference. But it's subject to all the same criticisms. So entropy is perfectly meaningful in lots of cases in information theory. There's no doubt about that. But as a way of choosing the prior, it doesn't solve any of these problems. Let's see, what else was I going to say? Okay, so the bottom line is people try to use this objectively, people try to come up with rules for doing it. I think in practice, you know, when you go to use software to do this, there'll be some built-in default, and that's probably what people use. Defaulted. Maybe that's not such a bad thing. There's also the hope that the prior won't matter too much. So in a finite dimensional model, a parametric model, if you have a parametric finite dimensional model, so it's a parametric model, the number of parameters stays fixed. As n goes to infinity, the prior matters less and less. And you can see that from Bayes' theorem because look at the form of Bayes' theorem. Let's look at the log posterior. What does the log posterior look like? Well, it's the log likelihood plus the log prior. This is some fixed quantity, but what's this? This is a sum of n things, right? The log likelihood is a sum over n observations. So what's happening is this keeps increasing, the effect of this term keeps increasing with n, whereas this is just like one observation. So what happens is that as n gets larger and larger, the prior disappears. In other words, if you had two people with two different prior distributions and you compute the posterior, you'll see them get closer and closer together as n gets bigger. And in fact, the Bayes estimator will approach the maximum likelihood estimator. And in fact, the posterior 95% interval will actually get closer and closer to the wall interval. So all the differences start to disappear after a while. And so in some practical sense, maybe choice of prior doesn't matter. However, this is only true for parametric models with finitely many parameters. As soon as you get to models with lots of parameters in them, which is what happens like in most modern problems, or non-parametric inference, the prior matters a lot in that case. And so I think that's a big change that's happened is in the 50s and the 60s, all the models were like 1, 2 parameters, and you had 100 observations, and really all these arguments were kind of more like how many, what's that expression, how many angels can dance on the head of a pin. There were sort of like irrelevant philosophical arguments because in practice it didn't matter much. But today, when we're dealing with problems with thousands or millions of parameters in them, all of a sudden those, you can't just say, oh, the data is going to wash out the prior anymore. So that's not true anymore. So, yeah, maybe I'll go through that in some detail. But let's talk about, so let's assume, however, that you've got a way of choosing the prior. So you pick a prior somehow, and let's suppose you know how to do the computing, you can compute the posterior. So let's put aside those concerns and say, okay, somehow you're going to pick a prior, you can compute the posterior, and so we can do it. The question is, does it agree with the frequentist answer, and what should we do if it doesn't? And let's just remind ourselves now again that they're doing two very different things. So let's concentrate, for example, on, for the moment, interval estimation. So if I'm going to choose a set C, from the Bayesian point of view again, that's just saying that given the data, the probability that I think theta is in C is 1 minus alpha. Okay? And again, it would probably be better if I put a different symbol here so that you'd say it's beliefs. Whereas what is the interpretation from a frequentist point of view when I do an interval estimate? It's the probability, let's keep in mind here now, from the Bayesian point of view, this is a random variable. The data are regarded as fixed. This is fixed. The only thing that's random is the parameter. It's the thing I'm making probability statements about. Whereas in our frequentist approach, we're regarding this as fixed. What's random is the procedure and the data. This is random. And furthermore, we're not conditioning, but we're requiring the minimum. We require that this is what's random. This has to track this no matter what the true distribution is. So this is the Bayesian statement. And the probability statement is about this, given this. Here, this is random, and we're saying it's going to track this 95% of the time, no matter what the true distribution is. They're very different statements. Coverage, this is frequentist coverage. This is Bayesian inference. And now the question arises, suppose somebody says, okay, here's my Bayesian method. I'm going to take a trial likelihood to get this thing. Imagine if I did repeat this experiment over and over. Would that 95% Bayesian interval cover the truth 95% of the time? The answer is no. It won't, in general. Nor is it supposed to, right? That's not actually a criticism of Bayesian inference because it's not designed to have frequentist coverage. It's supposed to just represent your beliefs about theta. So it might seem, though, intuitively, like, how can this happen? How can will this really not cover the truth? So I want to do some some specific examples that show you where the frequentist and Bayesian answer truly disagree. Because unless you see concrete examples, I think it's kind of hard to grasp intuitively that coverage and the posterior probability can be quite different. And there's lots of examples of this. In fact, I might even do one that's not in the notes. But let's start with the notes. So here's an old famous example. This is due to Charles Stein, Stanford University, and he did this in the 50s. Very simple example, which is we have a bunch of normals. We've seen this before a few times. This is called the many normal means problem. Each xi comes from a normal, but with a different mean. You even did a few calculations, I think, about this model. So I have n observations. Each one's from a normal of variance 1, but possibly different mean. And the question is, we're going to look at a Bayesian procedure and ask what the frequentist properties are. So first of all, I need a prior. And for this example, I'm going to do what's commonly done. I'm going to use a uniform prior. This is probably not a good prior to use, actually, in this example, but just for the purposes of the discussion, that's what we're going to do. You can compute the posterior very easily now, because the likelihood factors into n separate likelihoods, as does the prior, and so each posterior, it's not hard to see what the posterior is. It makes the mu's independent. You can see in the posterior, each mu I is independent, is an independent norm. Just by multiplying the likelihood times the prior, it all factors, so you can do each one separately. But now suppose, no problem, but suppose I want to estimate this quantity. And this is something, again, you guys did the calculations once about this parameter. So here's an interesting question. I have the posterior for the mu's is a multivariate normal. By using the rules of probability theory, you can now say what's the distribution of this quantity. You do a change of variables. Okay, so you can compute the posterior distribution of theta given the data. There's some calculations to do. But it's certainly a well-defined thing. No problem. And now the posterior ends up looking something like this. And I'm going to do a one-sided interval just for convenience. So this is the posterior. I can now find a number, C of n, such that my posterior, the probability that theta is in this interval, Cn to infinity, given the data, is, what did I make it, 95. Okay, so just multiply the likelihood times the prior, got the posterior. From the posterior for mu, I can figure out the posterior for this. There it is. I can find something that has 95%, and I can correctly say that according to this prior, at least, the posterior probability that theta is in the given data is 95%. So I've left out all the algebra, but conceptually I hope that's pretty clear. But now you can ask what's the frequentist properties of that Bayesian procedure. So imagine I simulate, I pick a theta, I pick a set of mu's, I give you some data, you do this, and you're going to get an interval. And now I know the true value of theta, and I can check, is it in there or not? And we could repeat it over and over and over again. And that's the frequentist coverage. And what Stein showed was how often, in the frequentist sense, so let's call it P sub mu, how often is theta trapped in here? So now I'm treating this as a fixed unknown constant. I'm just asking as a frequentist procedure. I'm asking if I simulated this, and count on how often. And what he showed is that this goes to 0 as n gets large. So if n was very big, it might not be 0, it might be, say, 0.001. So here's an example where if we report the Bayesian analysis, you might be saying this has 95% posterior probability, but how often does that interval contain the truth? Close to 0% of the time. It's not that there's anything wrong with either one of them, it's just, again, that they're doing two different things.
What was the algorithm for you?
Flat. And in fact, if we use a different prior, we could fix the problem in this case. We could make them agree. There are some cases where you can, so that's an interesting question. Can I pick a prior so that the frequentist coverage and the Bayesian probability agree? The answer is, I could have picked a different prior that would have made them agree here, but the problem is they would disagree for other parameters. Okay? More generally, if you're doing Bayesian inference and you're picking the prior to get correct coverage, then you're not doing Bayesian inference anymore. You're now doing frequentist inference. So there's an interesting, well, we can talk more about that later too. But I always tell my friends when they fool around with the prior until they finally get an estimator that has good frequentist properties, I say, congratulations, now you're a frequentist. All right. But the point of this is just to show you numerically these things can be very different. Okay? Let me show you another example. And this one is actually quite important. This came about, concern with this problem came about when people started doing clinical trials. And it has to do with the fact that when you do a clinical trial, when you have say a new drug you want to test, and you start giving it to people, often they're done sequentially. So what will happen is patients will come in, you might randomize them to treatment or control, and you keep doing it. And one of the issues that comes up in clinical trials is when you stop the trial, when you decide there's enough evidence that we should stop the trial. So stopping rules are a very interesting problem that comes up. So here's an example that is inspired by that. So we'll simplify it a bit, just say we have a normal, but think of this really, this is a mean theta, but really think of it as a difference of means. Think of this as the difference between treatment and control. That's where it really comes up. But just to be simple, we'll just say it's just normal, but we're interested in sort of whether there's a 0 or not. Okay. And I'm going to get the data sequentially. I shouldn't actually say x1 to xn. I shouldn't say that. I should just say x1, x2, blah, blah, blah. We don't know when we're going to stop collecting data. This, by the way, this problem we're about to talk about is something called selection bias. This comes up a lot now in a lot of problems. Like some of you may be familiar with network analysis, like social networks and so on. How you collect the data and how you decide to stop collecting the data can have a big effect on the inferences. At any rate, what's going to happen here is I'm going to collect the data, and as I go along, I'm going to compute. I'm thinking, intuitively, I'm thinking of testing that theta is 0. And I'm going to construct this statistic. So imagine, n, think of n as time. Every day I collect one observation, let's say, and I'm going to compute this quantity, which should look familiar. This is what? This is the wall test for testing whether theta is equal to 0 in this problem. But I'm just going to take the statistic, and here's my stopping rule. I'm going to stop collecting data when t is bigger than some constant, like, say 20. Let's say 20. So the way to think about it is, here's theta equals 0. This is k or minus k. And when x bar times root n is like way out here, I stop. Or way out here, I stop. Now, so the stopping time, the sample size is actually a random variable now. And this raised concerns because of the following issue, which was there was some concern that drug companies would do the following thing. I have this drug, maybe it doesn't really do anything. Maybe it's just like a placebo, but I'm going to keep testing it until it's like, saying this is bigger than 20 is like saying this is 20 standard errors away from 0. And so I'm going to keep going until it's 20 standard errors away from 0, then I'm going to stop. Well, that's going to always make it look like your drug is doing something. And So this seemed, not quite right. That somehow it would be unfair if we let drug companies stop their clinical trials that way. But something interesting happened. So you can see, first of all, there's a question of will this ever stop? Suppose the truth was actually 0. Suppose theta was 0. Will it ever will this ever stop? Maybe it'll never get that big. Because after all, x bar should be pretty close to 0, right? Do you think this will ever stop if theta is 0? Anybody want to take a guess? Yes, I wouldn't be talking about it. It's subtle, because it uses something we didn't talk about in this class called the law of iterated logarithm. You can look that up if you want. We learned the law of large numbers and essential limit theorem. There's other laws we didn't talk about, and this is called the law of the iterated logarithm. It's quite a subtle result, and we don't need to go through the details in this class, but from that result, you can prove that no matter what theta is, even 0, this is going to stop the probability line. If you simulate this, you are guaranteed with probability it will eventually stop. So the issue of whether it will stop or not, there's no issue. This is going to stop. You are guaranteed to stop, and when you stop, your test statistic is going to be way out here or way out here. Now, let's think about this from the frequency point of view. If I constructed a confidence interval the normal way, which would be x bar plus or minus z alpha 2 and root n, would that be a valid confidence interval? Would that have correct coverage? The answer is no, because I would have this little tiny interval out here, and if the truth was 0, the probability that it contains the true value is 0. Remember that a confidence interval to qualify as a confidence interval has to have correct coverage no matter what the value of theta is. This is why we require uniformity over theta. And so if the truth was 0, this interval will never contain the truth. The coverage is 0. So the correct frequentist answer here would be to do some sort of adjusted confidence interval to correct for the fact that we have this weird stopping rule. So we'd end up with kind of a weird confidence interval, but it would actually still contain the truth the right number of times. In particular, when we stopped over here, it would have to be a huge interval that sometimes includes 0. But here's the interesting thing. It's easy to show that the posterior is unaffected by the randomness of the stopping rule. It's a simple calculation to show that if you do Bayesian inference, the posterior distribution you get, suppose I had to run n to 10,000, let's say. The posterior distribution is easily seen just because it's the prior times the likelihood, and the stopping rule is a function of the data, and we've already conditioned on the data. So you can show that the posterior is the same as if we hadn't used the funny stopping rule. It's the same as if I had decided ahead of time to collect 10,000 observations. So what's going to happen when you have a posterior with a large sample and your 20 standard deviations from 0 is it's going to be very concentrated over here. That's what the posterior is going to look like. It's guaranteed to look very concentrated and be always, even if the truth is 0, it's always going to be concentrated far from 0. Because we stop when it means really far from 0. And so in that case, if I compute my 95% Bayesian region, it's going to look like something like this, and you can see that the coverage is going to be 0, because it's going to have 0 chance of covering the truth when the truth is 0. If this is confusing, you should actually try to simulate something like this. You can compute your posterior, you'll see it's always concentrated away from 0, even when the truth is 0. The coverage will be close to 0. And so this is just another example of where the posterior probability and the coverage are just very, very different things. And this is still controversial to this day because from the frequentist perspective, people say, well, this makes the Bayesian answer in this case not very useful. It seems like people can game the whole system here and say that they believe that the treatment effect is huge, when in fact it could be 0. And we're not even, we're going to miss 0 all the time. Whereas the Bayesian perspective is, this really simplifies things. I just take the likelihood, multiply it by the prior, compute the posterior. I can forget about why we stop. Trying to adjust for the stopping rule can be very complicated. Especially because, I made up a very simple stopping rule, but in real life, stopping rules are very, very complicated. And trying to correct for the stopping rule, it can be a very complicated affair. And one of the claims that people make in Bayesian inference is not worry about it. Just ignore the stopping rule. So depending on your perspective, it's either a feature or a bug, this fact that the posterior doesn't depend on the stopping rule. For our purposes, I just wanted to make it really clear that this is an example where they're very, very different. Where the frequentist answer and the Bayesian inference, Bayesian answer are very, very different. How are we doing on time? Oh, we're out of time already. Okay, so, boy, time flies. All right, so here's the thing. I need to summarize all this next when we come back from, well, what am I talking about? On Wednesday, we need to summarize this. I could do another example, if this isn't clear yet, but maybe you've seen enough examples. You want to see another example where you give different answers? Who wants to see another example? About 3/4? All right, so I'll do another example. It's not in the notes. It's actually a pretty cool example. It's called flatland. And it's just another example where the posterior and the complex interval disagree. Okay? And do you have any other questions that you think of in between? We can talk about them on Wednesday, because I know this can be confusing. All right, so I'll see you on Wednesday.